Hello friends, welcome to my channel. Let's have a look at problem 127, word lender. In this video, we're going to share a solution based on breadth-first search. First, I'll read through the problem statement to digest the requirement, and then we do a simple analysis to establish a connection of the current problem with the general graph problem. And then we share the code and explain the code in between. First, let's look at the statement. A transformation sequence from word begin word to word end word using a dictionary word list is a sequence of words from begin words to S1 to S2 and to SK, such that every adjacent pair of words differs by a single letter. Second, every SI for I in the range 1 and k is in word list. Note that the begin word does not need to be in word list. The third one is that the end string of word sk equals end word. So given two words, begin word and end word, and a dictionary word list, return the number of words in the shortest transformation sequence from begin word to end word, or 0 if no such sequence exists. So here are two examples. So in the first example, the return is 5. So the explanation specifies the path. So in the second example, the output is 0. So no valid path. So before we look at the connection, let's look at the constraints. First, the word length, begin word, end word, and the words in the word list are all the same. So their length is in between 1 and 10. So this is actually important information. And another thing to notice is that the word list length is bounded above by 5,000. So this actually also have to do with the problem size. So begin word, end word, and word list I consist of lowercase English letters. So this is also in some sense important because we are going to replace some characters in between when we build the graph. So the begin word does not equal to end word. So this is good if they are the same. So we just need to return 1 according to the problem requirement. So all the words in the word list are unique. So in some sense, so this word list actually plays the role of a set. So with that said, so we're ready to look at the treatment. So here we are going to use breadth-first search for shortest path problem. So this is actually a follow-up video of the video for Leetcode problem 433. So minimum genetic mutation. So these two problems are actually the same in essence. So you are welcome to check out the video for that problem. So here again, we interpret this problem as a graph problem. Here the graph that's denoted by G with edge set E and the vertices set V. So here V is the words from the word list, right? In other words, we want the word to be valid. And E is so the edge. So a direct edge exists between the two words if they differ by a single letter or character. So this interpretation transforms the problem to be a problem of finding the shortest path length between begin word and end word. So as such, so this problem is routine, right? So we can, for example, consider breadth-first search. So notice that the problem is shortest path problem. So we consider breadth-first search. So with that said, here let's look at the code. Let's share one format of solution. So first, I'm going to build the graph with the help of edge. So we can see this is a character replacement. So what I'm going to do is that I'm going to build a edge to words dictionary. So I'm going to use collections default dictionary. So I'm going to use list as the container. So we can use set also. So, but due to problem size, the list will be okay here. And then we're going to check for word in word list. So for this, this is a valid word, and then I want to compute edge, so which actually differs or use a dummy letter in the word at a certain index. So here I'm going to for I in range length word. So range word. So actually in this problem the length of this word is a constant, right? So but let's write in this way for the logic clarity. So then let's see the edge. I'm going to call this edge just the word. So ending at I. So we want to use a dummy character as long as this character is not lowercase English letter. So I'm going to use pound, and then we plus word. So from I plus 1 onwards. So this is something like the solution in video for Leetcode problem 433. So once we get this edge, then what we're going to do? So we're going to edge to words. So I'm going to use this edge as a key because this is string. String is immutable and it's hashable, so we can use it as a key. So we append word. So if we are using a set as a container here, so we need to use add method here. So this way we establish a map between a edge and the valid words. So notice that in this dictionary, the values are list, and the list contains a valid words or contains words in the word list. So this is the one part. So next, in order to run the breadth-first search, we need, if given one node, we need to know the neighbors, the direct neighbors. So for this, let me use a function to get the neighbors. So define get neighbors. So for this, I'm giving a valid words. So what we're going to do is the neighbors. So it can be multi-neighbors, direct neighbors, right? So this is very straightforward. So for neighbors, what we're going to do is that for I in range length word, and then we want to make consider an edge. So word I, and then plus pound. So this should be inconsistent with the above edge to word list the case, right? Here I'm using pound, so here we need to use pound. If, for example, we use star here, you need to use star here. So then plus word I plus 1, right? And then we're going to check for neighbor in edge to words edge, right? So actually we need to add this neighbor to the neighbors, right? So neighbors append a neighbor. So here I'm using append method. So actually we can use so similarly for this two line we can use edge. So not edge. So neighbors extend, right? So you can just put the edge towards edge, right? If the edge is not in the key, so this corresponds to an empty list due to the initialization of this edge towards. So with that said, so we actually can return the neighbors. So this way, actually, we established a graph structure. So then what we are going to do is to do the breadth-first search for shortest path. So this is very standard. Shortest path for That's not shortest path. BFS for shortest path. So in this problem, the return is the shortest path length. So we're going to let's see. We're going to do things like this. So we're going to use a queue. So here I'm going to use the deck subclass, and I use this deck as a queue. So initially we're going to consider the begin word. So in the begin word, if we count itself, it has a length 1, right? So this is the length. And then we're going to initialize a visitor set, so the set. So due to the assumption that the begin words so needn't to be in the word list, so I'm going to make some special treatment for begin words. So that is we regard it as start or visit begin word. So this is the queue initialization and the auxiliary set initialization. Next, we are going to do the standard while loop, while queue, and then we want to consider this level, and then we are doing radiation outwards in a cascading way. So for this, I'm going to first check for word level in queue, in the current level of queue, if there is one word equals the end word, and then we're going to return the level. This level actually corresponds to the length of the shortest path. So this is the one check. So otherwise, so we're going to consider next level. So for this, we need to pop we need to consider all the next direct neighbors of the nodes in the current level of the queue. So for this, what we are going to do is that we are going to consider the next level for, so let's see, in dummy index in length queue. So let me first get the current state of the queue. So let's call it n. Let's see, length of the queue. It's just one version of the writing of the code. You can try different versions for sure. And then we want to freeze this n, right? And then we pop n element from the queue, right? So what we're going to do is temp current and the level equals queue. So I'm going to pop left. Because here, if I pop from the end, so depends on how I append. So we are actually using different behaviors of the deck. So if we append at the end and pop at the very beginning, so this is a queue, right? Otherwise, we're going to use the stack behavior. So then this is the temporary current node, and this is level. And then we're going to examine the neighbors, right? For neighbor in get neighbors, the temp current, right? And then what we're going to do is that we check if neighbor not in visited, right? So if it's already visited, we do nothing, right? Let's write like in, okay, let's write this. So we're going to append, right? So we're going to append the neighbor, and so we want to increment the level by 1, right? And then this way, because here we didn't check visited, right? So here I'm going to visited add a neighbor, right? So typically you can also add this visited here before you check, either in the beginning or in here, or in here. Once it's in queued, we see it's visited. So with that said, so we finish the problem logic. And then if there's nothing returned during the while loop, so we're going to return 0. This is the problem requirement for the return. So with that said, we finish the problem logic. So in the big picture, so there are 2 steps. So one step is to build the graph. So we can actually sort of build graph on the air. We do not need to have a such a specifications. And the second one is the breadth first search for shortest path length. So this is the very standard. So this is the one flavor of this writing. And then we return 0 due to the problem requirement. And up to now, I guess this forms a solution format for this problem. We can do a check. So string index is auto range. So let's see. So words I plus 1. So here I missed a colon. So now let's check again. Neighbor is not defined. Do you mean neighbor? Yes. So now let's check. Here again we need to make a change. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases. So with that said, actually we finished sharing a solution for this problem. So here what we want to mention is that it's important for us to realize, or we can formulate this problem into a graph problem and identify the requirement to be finding the shortest path distance length, right? And then we write the breadth first search. So when we do the breadth first search, we up to the second step here. Then this is very routine now, and there are different ways of writing the solution. So here we provided one format. So this format is more or less similar as the second version for the problem 433. But when we build the graph, it's like the first version of solution to Leetcode problem 433. So with that said, I guess that's about it for this video. Thank you.